Can you hear me now? Yes? All good? Thank you for letting me know. So I see today we don't have many students. I guess it is Black Monday, yes? The day when students just don't show up. Now, how is my exam going? How many problems have you solved? Okay, 5, not bad. 3, not bad. Just try to keep it 1 problem a day would be wonderful if you can. And if you have any questions about any of the problems, to the best of my ability, I will explain them. Okay, so from somebody wrote easier ones, and I read it. I guess I haven't slept. I have hallucinations. I read it as I'm only working on the Easter problems. I think, oh, you don't really like my Hanukkah problem. Interesting. I was very proud of it, actually. So guys, one small thing is if the question is difficult and you are not making it, it's okay. It's not the worst in the world, right? I do not get angry when you are not solving all the questions. And my class is easy to pass to the extent that I think that you are actually working. When I do get very annoyed is when I know, not just think, but know that you are copying this question from the website or from each other, right? And if you do that, you will cause my irritation. And so please avoid that. And if I get irritated, and I know some people will do that nonetheless, so I might have this lottery. And I would prefer not to have a lottery, as I have more interesting things to do. Good. Now let's go back to the course. Again, guys, if you have questions about either your previous exam or the current one, after class, I'm happy to respond to anything I can. Good. All right, guys. So here we talk about Central Limit Theorem. It's a very interesting theorem, and we are not going to prove it, and that's unfortunate because we haven't actually we're not going to spend time on moment generating function in this class. I don't think we'll have the time, and those ideas are making those proofs easier. So first, let's observe that again, expected value of a sum is always the sum of expected values. And the variance of the sum is the variance of individual random variables summed if the variables are independent. Yes. And so if I want to calculate, let's say, the probability that x1 plus all the way to xn is less than b, this amounts to I can take the summation, subtract the expected value of the sum, and divide by the standard deviation. So what I do here is I make it look like a normal random variable. And the law of large numbers tells you the following. The law of large numbers tells you that if you have a sequence of identically distributed random variables that are independent of one another, then the sum converges to a normal distribution. You see, so that's what that's just a statement. It's an interesting statement, but and if you kind of learn a bit more of probability, you can prove it. That's just a fact. So take any random variable. It doesn't have to be normal. Doesn't matter what it is, and just if you just repeatedly perform experiments, and each experiment is independent, the average, the sum of the experiments is going to be a normal distribution. You understand? So here is, this is basically what you can do. You can just, to approximate this probability, you can apply the normal. That's one reason the normal is tremendously useful, right? You can just take this and you see what this is, right? This is This is just the cumulative distribution that the standard normal is less than this value. That's going to be an approximation. So here is an example of how that's supposed to work. Okay, so insurance company has 25,000 auto policy holders. If yearly claim of a policy holder is a random variable with mean 320 and standard deviation 540, approximate the probability that the total yearly claim exceeds 8.3 million, right? So the insurance company wants to know what's the probability this year it will have to pay $8.3 million on insurance claims. And how do we do that? Well, we have lots of random variables, right? Each person, each one of the 25,000 people is supposed to be a twin for this problem, right? So they are for us identical people. That means that they have the same probability that they will have an insurance claim. Make sense? So the total sum is the amount that person number 1 claims, person number 2 claims, person number 3 claim. And we know from past experience, we know that on average, the claim per person is 320. We don't right now know how they are distributed, but assuming that they're all the same, we have averaged them before, and we think that the average is 320. Okay. Make sense? 320. And the standard deviation is 540. So what do? We want to know what's the probability that total is more than 8.3 times 10 to the 6. And the total is approximately a normal distribution. That's the central limit theorem. Because we are presuming each claimant is independently going to file the insurance claim, and we assume that they are identically distributed, meaning that they are all identical people and they claim with the same frequency independently of one another. So this is what we then have. We have the expected value for T is just 320 multiplied by the number of people in the policy. Yes. And then we take T minus the average, and we divide by what? By the standard we divide by the standard deviation. And the variance is what? The variance is this number multiplied. So it is variance is this number squared multiplied by the number of people, by n, right? We remember it from here, right? Variance is the total variance is the variance of the individual multiplied by n. So here the variance, we take the square root of it here. So we just have standard deviation 540 multiplied by root of 25,000. Are you following me, guys? Yes, please confirm if everything is still okay. Wonderful. And we do that. You see, why do we do that? Because we want to apply the standard normal distribution. So we want the probability that this thing, that's approximately my z value, is bigger than this. So when you simplify, this is the z value is approximately bigger than that, which is approximately z value being bigger than 3.51 standard deviations, which is the same as 1 minus the probability that we are at 351 or below. That's the cumulative distribution, correct? You see why? Because we have symmetry. We don't even need symmetry here, because what is this? This is the probability we are at the right tail, and that's the same as 1 minus the probability we are at the left tail, at the left part. Yeah. So what we have then is that this probability is 1 in 1,000. So this amount will be once in every 1,000 years that this happens. Make sense? The probability is 1 in 1,000. That means essentially 1 in 1,000 years such a claim can happen. Beautiful. Now, this is something that you can do if you know very easily, if you know if you know moment generating functions. But here we are, for now, we're just going to say that if you have two independent normal distributions, one is x and one is y, each having mean mu x and mu y respectively, and standard deviation sigma x and sigma y, then the combined distribution x plus y is having an average mx plus my, and standard deviation root of sigma squared x plus sigma squared y. Yes. So this we can apply to the next problem. So let's suppose that we have a bridge, and this bridge can withstand the weights in units of 1,000 pounds. And that depends, of course, on lots of factors. It's also probabilistic. So how much the bridge can withstand before collapsing or before incurring damage is the random variable W, and that's normally distributed. You see, so today the bridge is strong, tomorrow the bridge is less strong. It's clear, let's say you're doing push-ups. So one day you can do 40 push-ups, the next day you can do 50 push-ups, right? And there is some distribution. So we're assuming that the bridge can withstand some amount of weight, but it's not always the same amount of weight. It can be more or less. And the distribution is in 1,000 pounds. It's a normal random variable. So it has mean 400, so it's 400,000 pounds, and standard deviation 40. You see, so in other words, the probability that the bridge survives without damage, let's say approximately 68% likely that the bridge survives a weight of 400 plus minus 40. Yes. 400 plus minus 40, 68%, it will not be, there will not be damage. Good. If the weight of a car is a random variable with mean 3 and standard deviation 0.3. Yes, exactly, from that. Yes, just to give you a sense what this means, right? So if the bridge is, if the bridge, the total weight of bridge plus things on top of it, so that's how much things on top of it can stand. If the total weight of things on top of it is 400,000 plus minus 40,000, 68% likely it will still not be damaged. Good, that's kind of what we just said. And with and then well, that it will, maybe I should say that it will be damaged, maybe, right? More likely that it will be damaged, because then if you increase the weight, it will be, probability is growing. So the other way around. So if the weight of a car is a random variable with mean 3 and standard deviation 0.3, so an average car will weigh 3,000 pounds, and standard deviation is 0.3, and that's also a normal distribution. So we want to know how many cars could there be on the bridge so that the probability of structural damage exceeds 0.1. So exceeds 10%. Okay. So how do we solve this? So we know that T is some normal distribution, and we know that W is a normal distribution. T is just the sum. We don't know if we don't even need to know that the cars are normally distributed. We just know that on average the car is, the average car weight is apparently 3,000 pounds with standard deviation which is equal to 0.3, I think, right? That's the numbers. Yes. Good. So T is normally distributed, the total weight of cars, approximately normally distributed. And W is normally distributed. So what we want to figure out is what's the probability that T is bigger than W, right? T is bigger than what the bridge can withstand. So what we have is t bigger than w. That's probability t minus w bigger than 0. You see, so here we have t plus the variable minus w. Each of them is normal. So then we calculate the expected value of t minus w. And that will be 3n minus 400. And the variance, you see, that's we calculated how? We calculated, we know the expected value of w, we know the expected value of t. T is the number of cars times their weight. So we have n cars, so 3n minus 400. Variance is what? Variance, they're independent. We're assuming independent. So the variance of t plus variance of w is this number, right? So it's n variance of x1 plus 40 squared. And when I simplify, I get this number. Are you still with me more or less, guys? It's a bit hard and my speech is impaired today. Yeah, so it's all kind of. If you have questions, let me know, guys. Anything unclear in anything I confused you in? Right, so just the only thing that I think I have confused you in is perhaps, well, maybe several things, but perhaps the notion of the variable w, right? So just you have to think, what is w doing, right? W is the amount of weight the bridge can withstand without damage. It's normally distributed. So what do we have? So what we have is the probability that t minus w is bigger than 0. It will be this is where we take it to be a normal random variable. So this is its average, and this is the standard deviation. And we do those same manipulations. If we subtract 3n minus 400 from the left, we do that from the right. That's what we have, this number, and we divide by the same standard deviation. That is going to be the z-square I want. So here it is. And I can calculate it by saying 1 minus phi of this number, right? Now, I want this probability to be, I think, bigger than or equal to 0.1 first, right? So I look in my table, when is this bigger than 0.1? That means I look in the table, when is 0.9 bigger than phi z, right? And for what value of z is it bigger? And that means we need to look at the inverse of 0.9 under the cumulative distribution. So then when you look into the table, you get that z should equal to 1.28, which means that we want a z-score that's below 1.28 or equal to it. Okay, so this is what we are looking for, and that corresponds to n being bigger than or equal to 117. Just now you can just solve a quadratic equation, you will get n bigger than or equal to 117. Here is another example. A coin is tossed 1,000 times. How likely are we to get 550 or more outcomes where the coin landed on heads, given that it is fair? That's question 8. Question 8, right? If we assume the coin is fair, what's the probability that we get 550 outcomes that are, let's say, heads? So we can approximate that by using the normal distribution, right? That's the idea here. Central limit theorem. We can say we toss the coin 1,000 times, so we have outcomes x1 all the way through x1000, and also the individual outcomes of each toss. Now, the expected value is, of course, of the sum. It's 500, correct? Because each of them is 1 with probability 1/2. So it's going to be 1/2 added to itself 1,000 times. So we get 500. That's the average. Now, the variance, each toss is independent. So the variance we know is 1/4, right? Remember, the variance is 1/2 minus 1/2 squared, correct? For each individual. So the variance of x1 is 1/4, variance of x2 is 1/4, and the summation is just 1,000 divided by 4, which is 250. So the probability that the sum is bigger than or equal to 550, it's we can just subtract the average and divide by standard deviation. We do the same on the other side. And what do we get? We get the z bigger than or equal to 50 over 5 root 10, or probability that z is bigger than root 10, or probability that z is bigger than or equal to 3.16. Yes. And then what do we do to look at it in the table? We just take 1 minus this number, and we get 1 minus 0.9992. And what we get is essentially 1 in, so we get 8 in 10,000. So the probability that you will get that result, if you simulate this experiment, if you simulate this experiment 10,000 times, you will get about 8 of them with 550 or more. Make sense? That's an estimate. Let me know, guys, if you can still follow. Now, question B. This is the next question, slightly different question. Now, first, notice I assume the coin is fair, right? If the coin is fair, the outcome is not likely, but that's the outcome if the coin is fair. Now, the question is, suppose that this is what you got. You don't know if the coin is fair or not, and you tossed it 550 times. Is the evidence enough to conclude that the coin isn't fair? That's the question in B. You understand? So let's look at this question once more. It relates a little bit to something you do in the exam. You don't need to use this, I think, but it relates to some ideas that you have on the exam. So what you have is A. We have x bigger than 550, given that coin is fair, that we know. It's 8 over 10,000. So it's rather unlikely, and therefore you are tempted to reject the hypothesis that the coin is fair. But however, let's, before we actually answer this question, consider another example. I just want to see what you would say in that other example. So a teacher is working in Children Are My Sunshine inner city school, where there are 101 pupils. 101st pupil is Dennis the Menace. So there was a prank performed. Dennis the Menace is again going to be likely to be performing a prank more than other people, right? So it's known that only one of the students perpetrated the prank. Only one was guilty of it. And if Dennis were innocent, the probability that of such prank would have been 0.001. In other words, if Dennis is innocent, the probability of this happening is 1 in 1,000. So he's always causing problem. And when he is innocent, when he's not causing problem, there are very few problems around, so to speak. Yes. So the policy of the school is to regard the student as guilty if the probability of innocence is below 5,000, 5 over 1,000. So the question is, what should they do? I mean, should they find him guilty? So let's say if I missed some. So suppose that what you do is you look into the information available, and you find the following. So you have a registry of people that committed prior offense, and you have about 9,001, and out of them, on average, one will play spins on the chair as a prank. It's also estimated that every good pupil is going to do that with probability 10 to the power of -5. Okay, so less likely, right? So let I be the event that Dennis is innocent, and E be the event that this crime is committed. So we know that probability of innocence approximately will be maybe 9,000 divided by 9,001. Probability of evidence given innocence is 10 to the -3. Probability of evidence given no innocence is, of course, that he is not innocent, there would be this evidence, so the probability is 1. So, and probability of evidence given innocence is equal to the probability that one of the 100 good pupils committed the prank, right? And if you actually calculate using those numbers, you can calculate the probability that Dennis the Menace is innocent given the evidence is the probability of evidence given that he is innocent, probability innocent divided probability of evidence given innocent, probability innocent plus probability evidence given innocent complement, probability innocent complement. And what you get when you plug in those numbers, you will get the number to equal 0.9. So it is 90% likely that Dennis is actually innocent. Yes, I'm sorry if it doesn't, how do you say, strike you. I bet you're about to faint. At least that's how I feel. But it's, so yes, only 10% that he is guilty. And yeah. Yes, that it's by another student. It's essentially, if you have many rabbits, many bunnies, right? I mean, what are you more likely to die of, a lion or a rabbit, right? So there is some small probability that a rabbit is going to kill you, correct? That's the idea. I mean, we can calculate. Apologies for my, what is it, effervescence? I'm not sure if that's even the right word here, but yes, I'm flying also in other spheres, just like you are, unfortunately, right? So for this problem, it's essentially this. Intuitively, you know that a lion is much more dangerous to you than a rabbit, right? But there is some probability that a rabbit will kill you. Maybe it will bite you in the neck in the right place. I don't know, right? There is some probability that a rabbit will kill you, but it's tiny, tiny, tiny. Now, the thing is, you can make the likelihood that you will end up dying from a rabbit much more likely by having many rabbits. You see? So, if you have one lion, but you have trillions of rabbits, it's much more likely, actually, even though in each individual rabbit is unlikely to kill you, but it's much more likely that one of the trillion ones will. It's like, you see, the difference is you perform an experiment with very low likelihood of success, but you perform it so many times until success actually occurs, or you perform an experiment that has a very high likelihood of success, and you do that very few times. Right? So you understand there is a balance, right? A lion is very likely to kill you, right? Compared to a bunny, but you don't meet lions very frequently. So you meet a lion once, let's say you pet a lion once, as opposed to you pet 100,000 bunnies, you understand? So, or 200,000 or a million, whichever that number is. So that actually ends up, it's not very paradoxical, but it seems paradoxical to some people perhaps, but the very non-dangerous mundane things are very, very terribly dangerous. And since you're falling asleep, I'm very tempted to play to you a song called, in Hebrew, it's called the Guardian song, right? Because it's specifically about that. Protect yourself, protect your soul from that which is close and beckoning, from that which is as close as the sky and the ground, right? So maybe poetry will wake you up. Very beautiful song, which I sometimes hear at night. It's very rare, by the way. My dreams are tremendously scary and always visual, guys. Extremely visual. I mean, if you actually knew what I dream about, you would understand why I sleep so low, so infrequently. My dreams are truly, yes, but they're visual. And then one time I had an auditory dream, and it was the voice of Chava Alberstein. And if you want to hear that voice, I can play that song for you so that you wake up perhaps, or maybe fall asleep much deeper. Tell me if you would like that, or we continue with, we obviously have to continue with more probability, but I am just trying to hold myself and you as well together, as I know I am being boring today and that bothers me. More statistics, I see, no poetry for you. That's too bad. It's very, very sad, guys, that you do not know who is Chava Alberstein, truly, right? Truly, truly sad to me. I'm not sure if it will help you knowing it, but yes, I think honestly that you don't know it, maybe your life is not worth living once you realize what you miss. Yeah, but that's because you studied it. You don't study poetry, you know. You either feel it, understand it, and it moves you, or you do not. So never study poetry, and the people that teach it don't know anything about it, right? Well, that's really terrible. What can I say? Don't go to school. Okay, so we'll do more probability since you don't want to listen to that Guardian song. All right, here is an actual case. Okay, guys, an actual case. Very interesting. I actually recently found out what happened to Sally Clark. She is no more. She committed suicide. Here is what happened. In 1998, Sally Clark was tried for murder after 2 of her sons died shortly after birth. During the trial, an expert witness for the prosecution testified that the probability of a newborn dying of a sudden infant death syndrome, it's called SIDS, was 1 in 8,500. Okay, so the probability of each individual child dying, you know, just a random child dying, I guess, right? It would be 1 in 8,500. I presume the way the probability is calculated, if at all correctly, is that you look at causes of death of children. So you have a bunch of children and you look at causes of death, and out of 8,500, there is one that you call SIDS, whatever that is, right? Sudden infant syndrome, right? You always have to wonder how this thing is calculated. Correct? It can be very misleading otherwise. It's very difficult to get the right information. So she actually had 2 children die. And what this expert did, he multiplied 1 over 8,500 by itself. He took a square of it. You see? So he thinks, okay, 1 child dying of SIDS, he thinks that it's independently the next child will die of SIDS, and then you multiply the probabilities. Yes? So when you multiply the probabilities, that means that the probability that 2 children are dying of SIDS is 1 in 73 million, very low, okay? And therefore the conclusion was, of course, well, the probability of innocence is low, the person is guilty, jail. And she was convicted. And my God, my guys, this is that people convict without understanding probability. It's horrible, right? At least understand probability. At least look at the evidence. My God, you know what we descended into? We don't look into the evidence at all. We just voice opinions that are completely meaningless because they are not justified in anything whatsoever. And that's a terrible non-intellectual thing to do. And it's done increasingly frequently. So let's understand what happened in this verdict. So first of all, what things have been confounded? What errors are in the argument of the prosecution? So first of all, death due to SIDS, obviously, guys, if it's in the same family, there is no reason to assume it's independent, right? It's maybe there's some genetical factor. So maybe it could be that if one child dies in a family, then the second child dies also with virtual certainty. You understand? Because what's independent? Independent, I said, or independent kind of very like independent is in the general population. If you take two parents, if you take parent one and parent two, and they are not related, the probability that both of them will have children dying due to SIDS is maybe 1 in 73,000, maybe, right? If you take two of them. But if you take one parent and you know that it already happened, perhaps, I mean, she is already carrying this particular illness, or it's genetic illness, or whatever that else that might be. Good. Now, the second part is there is confounding between probability of evidence given innocence and innocence given evidence. You understand? They are not the same. Right. So the argument was that the evidence is unlikely if a person is innocent, but the evidence occurred. You understand that people confuse that. It's called, by the way, the prosecutor's error. Right. You understand? So you think, okay, given this assumption, the evidence is unlikely. Right. That is important. It can affect the probability, but you have to remember evidence occurred. Unlikely or not, you are in that universe. So you have to, in the reverse, think what's the probability of innocence, right? Given the evidence. We know evidence occurred. We don't know if innocence occurred. You understand? Those are very different things that people always misconstrue. You understand? If I throw a coin, we spoke about it, and the coin, I threw it 1,000 times, and 1,000 times I get heads. You say, well, I don't believe you that the coin is fair. Why? Because the evidence is extremely unlikely, tremendously unlikely if the coin is fair, almost impossible in the universe. You understand? You will be in this case correct, but you still have to understand why, right? You still have to reverse it. What's the probability that the coin is given this evidence? What's the probability that the coin is fair is different from evidence given the coin is fair. You understand? So here is the calculation. So what is needed is the probability of innocence given evidence, and that ends up being the same. You can see here, it relates to evidence given innocence. It's evidence given innocence times probability of innocence divided probability evidence given innocence times probability of innocence and whatnot, right? You know, let's just reverse it. And what happens? This number can actually be very high. Because, for instance, maybe the probability of innocence initially is very high. You understand? Very few mothers will harm their children. It's very rare for them to harm their children. So probability that a mother is not innocent in the murder of her child is tremendously low, and therefore the probability that she's innocent is tremendously high. So you see, so there is a combat between this probability, which is small, and this probability, which is high. You understand? It's not obvious which wins at all. And especially that the probability of SIDS is not 1 in 73 million. You understand? I mean, if this is tremendously small number, then it's more likely to offset this probability. You understand? That's why you don't believe that a coin tossed 1,000 times that turns heads is a fair coin, because the probability of that is so small, you believe it will offset any other probability that will make it likely to be a fair coin. You understand? But you have to really have this comparison. Okay, so this information is required. So in essence, she was convicted on false charges and placed in jail and later released, but it never helped her. Understand? Can you imagine a person lost 2 children, almost certainly innocent, placed in jail, afterwards released. I don't know if there was compensation or not, but I think the person never recovered from it, maybe never recovered from the loss of children, and that's it. The person committed suicide. And what I find very interesting is since several years already, I see trial by mob all the time. Trial by mob, right? Just you have people screaming something and not looking to any evidence and just like their emotions and nothing else, no brain. And that's where we are living today. It will be worse, don't worry. Yes. I'm always very positive. But you will be better, right? You will know probability. You will be very good thinkers. You will surprise your opponents, correct? That's my hope. So here we go, guys. This those questions. I mean, I was spent I think 10 days in summer in some country club, and I was just very surprised. It was a while ago how they managed to, let's say, deliver foods to you that you might order it again and again. And I even worked in catering, and it was always interesting to me. How do you figure out how much ingredients to buy? Right, and because people sometimes prefer one meal over another, and how do you ensure that essentially everybody has as much as they want to eat? Yeah, well, I have nightmares about that, at least until recently. I feel bad for every waiter that ever worked in a waitressing job. Well, they do menus, sure. I mean, some of them you already know how much how much people want to order, right? So let's say if you maybe work in catering, the client might tell you how much to get of each, right, of each ingredient. But imagine in a country club, what you have is you come to a country club and you don't know what's going to be on the menu, right? And you see a menu, and then let's say you want the same dish maybe twice or 3 times, right? And very frequently they will oblige, they will give you the dish. You understand? They seem to have enough of it, right? And then I thought, how do you estimate how much to make so that you don't waste as much? Yes, for the food services, I don't know how people can live for themselves to work in any service industry. Very difficult. I worked a little bit, I hated every second of it. My favorite job was at the aquarium. You know, I was working with sharks. You know why? With sharks and horseshoe crabs. I mean, what 2 things I don't like? Well, I don't like people, but I also don't like children, especially the ones that ask boring questions like, oh, does it bite, right? So you have here's a crab. Do you want to touch it? No, then get the hell out of it. And then everybody, oh, there's a penguin, and they'll leave you alone. You know, you could sit there by the tank, and I would prefer the cold water. Freezing water over dealing with people and children, right? This work I really enjoyed. I would also have a timer. You know, you have this starfish, and by the time the starfish crawls to the other edge of the aquarium, it will be like 5 hours. I can go home. You know, so it's like you put the starfish on one side of the aquarium, it slowly crawls to the other, and then that's it. It's like that's your clock to punch out. Well, yes. Well, I am truly impressed, Barry, with people that survived it, that actually managed to do that and be happy, right? Or even for a little bit, yes. Because dealing with people is pretty unpleasant, right? And food industry, yeah, catering industry, any of it, I don't know. it's almost as unpleasant as teaching in high school or in elementary school. That's my worst nightmare, right? Why not high school, Nicholas? Well, it depends. I mean, I would be happy to teach you, I mean, right? Or people like you, but most people in high school, they just don't care. And more worse than not care. Right. So if it's easy and pleasant to deal with intelligent people, right? Because you can talk about so many interesting things and they're enjoying your company, hopefully. And not all of them, but some. And yeah, it's and then they actually give you things to think about. Whereas let's say I had an uncle and he taught for some years at a special school, and he would go, this is an envelope. It has 4 corners. On the envelope, it says, Lilia, that's your mother. Give it to your mother, something like this, right? So that's how we spoke. You see, and that can be. That's why I don't want to teach in high school. Anyhow, guys, so let's go back to. I hope you're woken up enough. Stuyvesant. My brother went to Stuyvesant, was very, very driven, and now he's trying to force me to eat marijuana, right? Just tries to make me smoke stuff. So you see, that's what happens after a person goes to Stuyvesant. To some of them, at least. All right. So here we have this thing. Of course, it's a bit crazy. I had a few students from Stuyvesant, but I enjoyed them. You know, they're masochists and they don't complain. You can just burden them to death, and they will just say, "Yes, I'm enjoying it so very much." You know, right? Like, okay, do you find it difficult? It's like the equivalent of 400 pounds. No, I want to be like this all my life. You know. So it's a pleasure, you know, you put the extra weight on them, you know, like here is a more difficult exam. Like, thank you so much. All right. Well, I don't know what they enjoy. I think they're afraid of their parents. They also tutored, you know. So I had people that were just like, he only got 95, and they would bother this person for 95. Anyhow, guys, here we go. Back to probability. Ideal size of a first-year class at a particular college is 150 students. On average, 30% of those accepted for admission will actually attend. Okay, so it's known on average 30% that you send invitations, they will attend. So you obviously want to approve more applications than people that you would admit. Isn't it interesting, right? So then you would approve 450 students. And the question is, what's the probability that more than 150 first-year students attend this college? Understand? We don't want more than 150. And what's the probability that can actually accidentally happen because we admitted to many? Good. So we again imagine all the students to be the same, which is another reason I don't like the education system. That's exactly what they do with teachers. The students, they imagine they're all twins. Right, so x1 is person 1, x2 is, and we imagine they're exactly the same, and each of them will attend the school with the same probability. So with probability 0.3, 30%. Yes. So what's the expected value of total number of people that will attend? It's 450 multiplied by 0.3. Agreed? That makes sense, yes? This one is 0.3. This one is just you add 0.3 450 times. That's the average, right? You see what we do? We don't know how they are distributed, but we know the variance, which can be calculated for many random variables, right? Pretty interesting. I mean, it can be estimated. Variance is essentially an average, right? You just can if you have a table, you can estimate it. And so what do we know about the variance? Each person is either attending or not. So the variance is 450 multiplied by 0.3 multiplied by 0.7, right? you might remember it. It's a binomial random variable here. If it's independent, we know that even x is a binomial random variable, and what I put here is the variance of the binomial. Yes, but you can calculate it directly from each of them. It's up to you how you do it. Make sense? So then we want more than 151. So it's 151 minus this number divided by this root and whatnot. And what is this number? This number is approximately 1.65. So the probability that z is bigger than 1.65 is about 0.05. Yes? You know how to calculate it, right? We just take 1 minus the probability that z is smaller than this number, and that's what you will get, 0.05. So about 5% likely that more than 150 students will attend. So not a very likely event, and they decide it's worth the risk. Okay, then I have this another problem about something in engineering, but I guess I will skip it. I don't want to bore you too much. I will go to the next lecture. Good? You can read it afterwards. So beta distribution, that is interesting. I hope I will be able to convey that it's very interesting. So you see, guys, very often you do not know the probability of some event, and you are trying to estimate it from experience. Well, hopefully not too difficult. We'll try to understand why it works. So if you understand why something works, it's less difficult than if you do not understand why it works. Yes. So what's the idea of beta distribution, guys? You are trying to estimate. You're trying to estimate the probability of something that you do not know, right? You don't know what's the probability of before you begin the experiments, before you have some evidence. Okay. So beta distribution is a continuous distribution on the interval 0, 1. It is a generalization of the uniform variable over 0, 1, and it is defined like this. It's defined as x to the a minus 1, 1 minus x to the b minus 1, where x is between 0 and 1. And what is this? This is just the corrective factor, because from 0 to 1, it has to integrate to 1. You understand? So it's 1 over the integral of x from 0 to 1 of this expression. Here it is. Good. And beta distribution, essentially, it can have essentially any curve over the interval from 0 to 1. And here are some examples, right? So beta 1, 1 is a horizontal line. You see, if I put 1 and 1 here, then it's x to the 0 and y to the 1 minus x to the 0. So that will give you a flat line. You understand? So it's essentially take the standard uniform distribution and you can distort it. You can make it like this. You can make it like this. That's for a bigger than 1, b bigger than 1. You can make it like this, like a heel close to the left, a heel close to the right. You can make it a straight line. You understand? It's just extending over the interval 0 to 1. And I'll try to explain to you why this distribution is very interesting and useful. Good? All right. So first, we are going to have this proposition. We want, in some special case, where the power of x and the power of 1 minus x are integers, not just any numbers, but integers. We want to understand very quickly how to calculate this integral. So this integral, n choose k, x to the k 1 minus x to the n minus k dx, happens to be 1 over n plus 1. Okay, and we will try to understand why that's the case. That's pretty cool, guys. I like the idea that, you know, instead of doing integration, which can be annoying or difficult, you can figure out what's the value of the integral by using a combinatorial story. Like that's what we did for some questions there. So here is the idea. So randomly pick n plus 1 points on the unit interval from 0 to 1. Color n of these points black and 1 point red. Okay, so the points are small. They are like atoms. So then we define, here is the picture, right? So then we define a random variable x. We see that they're essentially, we have n+1 of them. One is red and the others are black. Make sense? Here is a picture. You see here the n black and one is red. Good. Now x is 0, 1 all the way to n. It's the number of atoms to the left of the red one. You see here is a red one. We can have a bunch of them. We can either have 0, maybe red is the leftmost, or we can have 1 or 2, or who knows how many, right? All of them could be to the right, right? So here it is. Okay. And then what do we know? So what's the probability that x is equal to k, given that red is in position p? Yes, if red is in position p, do you see that the probability of success, they're randomly placed. So each of them is randomly placed. So the proportion placed here is p, and the proportion placed elsewhere is 1 minus p. Do you see that? It is p. Basically, if each of those trials, if each of them is randomly placed on this interval, we now by this p, we now divide it. That's why it's p, right? We now have this region. Proportionally, if they're uniformly placed, this has probability of p of being placed, and this has probability of 1 minus p being placed. Yes, if it's completely random there. So the probability that x equals to k, given that red is at p, is n choose k, p to the k, 1 minus p to the n minus k. Do you see where is the n when choose k comes? Which of the n? They are kind of 1, 2, all the way to n. Which of them are to the left? Each of them independently is to the left with probability p, and to the right with probability 1 minus p. So here it is. N minus k are on the right and k are on the left. So far good, yes, guys? It's easier a little bit than what we had before. Okay. So we know that we have a uniform random variable, and the density function is 1. Do you agree? Because it's uniform. If we're saying it's equally likely, how do we simulate equally likely? Understand what happens in my head? In my head, equally likely means that if I imagine the intervals very small, discrete, then each of those subintervals are going to have the same bars, the same bar graph. And the bar graph is reaching to the same elevation. So you can see that the skyline is a flat line. And the line has to be at 1 because we have to integrate to 1. The full box probability is 1. Agreed? So this density function is 1. And we can calculate the probability that x is equal to k. That's what we want. You see, guys, here is what we know. We can calculate x equal to k, given that red is in position p. But suppose we don't know where red is located, and I want to calculate probability that x is equal to k. Yes? What do? I here try to explain to you that I do the discrete approximation. That's how I think. I can do it even faster by using dx instead of those symbols. But the idea is, suppose you partition the interval, this interval, you partition it into m segments, where m is maybe million. If it's million, you will not see it. It will look to you like it's smooth, right? You partition it into m, and then you use Bayesian statistics. You see, probability x equal to k, given you are in region R1, or region R2, or region R3, right? Region R, it should be, I think, region Rj. Rj is j over m, not Rm, but Rj, right? So you understand what's happening here. So here is R equal to j over m. What's the probability that x is equal to k then? That's the probability that's the probability j divided by m to the k, 1 minus j over m to the n minus k. Do you agree? There are some glitches and some typos. I can, if you want to write it on a separate white paper, on the separate whiteboard, would you like me to do that, or you follow this information as I wrote it? Okay. So be careful, guys. Some of those were written in a hurry and they have typos. So here is the idea, right? I want the probability that x equal to k, but it's hard to calculate this probability without knowing where the red point is located. You see, here I want the probability that k black points are before the red point. Right? Now, how do I do that? Well, I look at the interval, right? And I will do it slightly different. And let's say here is a region. This region is dx. That's how I actually tend to think. It's a bit easier than writing the full Riemann sum. This region is dx. What do I mean by that? I mean that I'm dividing this interval into many segments. You see, many segments. So at dx, this is position x. So it means that that the red ball is in position x. Red is here. Good. Now, if red is here, then for instance, we have the probability that x is equal to k, given red is in position x. That's what we have here, right? That's known to us to be n choose k, and the probability n choose k. Then we have what's this distance? The distance is x, so this is x to the power of k. You see, because if red is here, then the probability of success is x, and the probability of failure is 1 minus x to the n minus k. Good? You with me, guys? Now this is so how do I write? How do I do when it's x equal to k and r is not necessarily x? So it could be for various values of x. So that's the same as the summation. I'm using Bayesian summation, where r is at any different position x. I'm just going over all positions x. So what I mean by that is there is x1, x2, x3. You understand? There is this x1. Here is x1. Here is x2. Here it would be x3 and onwards. You understand, right? So it's for all the position. I mean, I'm saying you understand, but do you understand? I need to catch myself. I say you understand, right? And maybe it's wrong. Yes. So this is an x, and what I have here is probability that x, capital X equal to k, given that r is equal to x, probability r is equal to x. Where probability r equals to x, it's continuous. It will be 0, but I approximate. You see, what is for me probability r equals x? It is here, right? Probability r equals x to me is, I interpret this probability as r being between x and x plus dx. Make sense? And that probability is what? That probability is simply dx, because we're using uniform random variable here, right? So it's just dx. So what do we get? So we get summation over x n choose k, x to the k, 1 minus x to the n minus k dx. And the summation is nothing more than an integral. So what we get, this is the same as the integral from 0 to 1, n choose k, x to the k, 1 minus x to the n minus k dx. Yes? You see what we have done, guys? We haven't solved it. We just gave one interpretation. You see, we can solve the Biller, this red point, black points below. We can solve it using this integral by story. But instead of solving it this way, we come up with a different protocol or a different procedure how to do it. So do you agree, guys, that the red point is equally likely to be anywhere, right? So basically, if you just throw the points, the red point is equally likely to be first, second, third. There is no preference to it, right? And because of that, it's equally likely to be in any of the, maybe it's the first point or the second point or the n plus 1 point, right? So the probability it's the k plus 1 point. This is also the probability that red is a k plus 1 point. right? And the probability is the k plus 1 point is 1 divided by n plus 1, because it's equally likely to be first, second, third. You understand? I use symmetry here. By using symmetry, I can clearly see there's no preference, right? Each point, you know how I know it may be a better way to see it. You see, each point is equally likely to be first. There is no bias, right? It's like you're supposed to be true American. So what is true American? It means that everything is equally likely to be in any place. So first place, anyone is equally likely, right? That's the idea. Good. And if you're not American, of course, it confuses you as well, right? You don't have it. Makes sense? So this is 1 over n plus 1. That's how I do it. Here I solved it slightly differently, but it's much simpler. The way I explained to you, I think now is how do I know the answer is 1 over n? Because this is asking what's the probability the k plus 1th point is red. They're scattered, and what's the probability the k plus 1th point is red? Now the k plus 1th place is equally likely to be taken by any of the n plus 1 points. Understand? So I just focus, I don't even focus on all of them, I just focus on the k plus 1 position, right? The k plus 1, who is going to be first, second, third, each is equally likely to be in any position. Good? And this is what we have been able to figure out, guys. Look at it. So this tells us that this integral, if I use a and b, so here I have a minus 1 and b minus 1, and therefore it's a plus b minus 2 altogether. If I add this plus that, it's a plus b minus 2. Choose a minus 1. This is going to be 1 over a plus b minus 1. And so I can now calculate easily what's the beta value for an integers a and b. So this integral from 0 to 1 is just missing this part. So it's really what? It's really this number divided by this number. When you simplify it, it's going to be like this. Isn't it nice, guys? So to integrate x to the a minus 1, 1 minus x, b minus 1 dx, when those are integers, this is what you will get without doing any calculations. You can do it by repeatedly doing integration by parts. Maybe you can use the computer. I'm not sure what answer the computer will give you. I mean, they're powerful computers, smart computers as well. But here, without any calculation, you know this value. I always enjoy it, right? You solve an integral because you realize it talks about something, right? It's like realizing what something means because you understood what it's called for. Okay, so here is an example that we will try to understand why the beta distribution is useful. Okay, this is going to tell us how to update our estimate of probability. So suppose we have a coin that lands heads with a known probability p. I do not know if the coin is fair, unfair, I know nothing about it. And I want to figure my prediction based on the outcome. I say, how likely do I believe the coin to be fair based on evidence? You understand? Related, similar to one question we already solved about coin landing 550 times, right? And what's the probability it's fair? So here we go. What do we do? So suppose that we are going to toss the coin n times. And of course, the larger the n, the more convinced we are going to be about the actual probability. And we're going to gauge how many successes we have. Okay. Mm-hmm. So the default assumption with which we can start with the default assumption that it's equally likely to be of any probability. You agree? I mean, it's not, doesn't matter if it's true or not. You will see that you can update it, right? But you can have the naive assumption that it's equally likely. You don't know anything about the coin. It might always land heads, it might always land tails, and it might do anything in between. Yes? So what is the probability that if we perform n experiments, we have k of them are heads. We're going to try to understand how to interpret the probability, given that, let's say, we perform n experiments, k of them happen to be heads. Make sense? K could be 0, 1, 2, I don't know, maybe if n is 10, k is 5, right? We will figure out how to interpret this. So here we go. So let x be the number of successes, heads, and if we give the density function to be like this, to be you see, why do I use this? It's a more general one. I can of course start from assuming it's equally likely, but in general I can this is a particular instance of this density function. So I might as well assume that the probability distribution of the coin, you understand what I mean by probability? I can never be certain by just having it a few times what's the actual probability, but I might say maybe it's very likely to be 1/2. Let's say if I tossed it, I don't know, I tossed it 1,000,000 times and the result is 500,000, I might be very certain it's close to 1/2. Yes, it will kind of shrink around it. Maybe I can find a simulation. Let's see. Here we have beta, right? So let's say here is what we're going to do, right? Let's try for a moment to see what will be the distribution if we toss the coin, let's say 100 times, right? 100 times, and we have let's say and we have 50 of them are successes, right? Let's say 49 are successes, and 51 are failures. Okay, and then here is the graph of the beta distribution. You see, it's around 1/2, right? You can see that the estimate is between more or less it disappears, right? The estimate is between 0.35 and 0.65, maybe even less, right? Now imagine I have I add. Maybe I will have here, maybe I have, 1,000, right? So then I have this, and let's say we'll have 500 and 500, maybe 499, and 501, right? And you can see it kind of it shrinks. The probability is shrinking. It's no longer likely to be around 1/4. You can see, probably you need to zoom around it. You can see the variance is very small. You see here's the variance. It kind of shows you this graph, but you can see the variance. Essentially, it's zooming in around 1/2. It could still not be, might be something else. We don't know that it's truly 1/2, but we have an estimate. You see, we are very convinced it's not 0.2 or 0.4. And we think the probability is between this interval and that interval. And the more experiment we have, the more certain we become about the true probability of this coin. It kind of shrinks to a line around the actual probability, right? You understand, right? So if I have 2,000 here, let's say maybe we have 1,000 here, and 1,000 here, and you can see that it shrinks even further. You can see, right? It's the variance is shrinking further. It looks similar to the graph, but essentially it's like one small spike. Good. You understand how that's supposed to work, and we just have to verify that it actually does what we wanted to do, right? So the natural place to start is, of course, to assume that it is distributed by this by this beta distribution. You know that the probability is beta, and why? Because it's very flexible. You see, I mean, I can say I can just adjust A and B, and I can make the curve pretty much almost any curve on the interval between 0 and 1. I can have a lot of variations, but of course the natural assumption is, of course, to set A equal to 1 and B equal to 1 to say that it's uniform. Initially, I have no idea what it is, so I'm suspecting my null hypothesis, every outcome is equally like. Yes. Now, so then what you have is then you can derive this. I would, no, maybe I will finish it next class, as I think my time is up, unless you really want to hear the explanation today. I bet you don't. But think about it, okay? So it's a very, very important distribution to understand, very interesting one to understand, because it allows you to figure the methodology for understanding probabilities that you don't know. I mean, many events, you have no idea what's the probability, but you can see how many, you just perform a bunch of trials, see how many of them are success, and you have an estimate of what's the probability. So for instance, how do you estimate how prevalent a disease is? Which is very interesting that it's not done here. I mean, if anything, you know, everybody started going and testing it themselves every freaking day, all the time. That's not what you do when you do probability. You know what you do? If anything, you take a random sample, take 1,000 people and test them. And that will tell you, because it's a random sample, it will tell you the distribution. It will create a beta distribution. It will tell you how prevalent is the disease in the population and test them thoroughly, perhaps, right? But they do it for 100, 1,000, whatever quantity, but you don't need to rush everybody there to get tested. That's a meaningless, stupid thing to do, right? As many other things are. But anyhow, so I will pause the lecture, guys. And if you have any questions, or you want to listen to Chava Alberstein, or I don't know what else moves you, then we can do that. If not, goodbye.